when I consider as an engineer as well as a mathematician, basically my training has enabled me to look at systems, to look at logical interplay between systems. And when you come as an engineer, you can see immediately a system, and you can see that there has to be a mind behind it. When you look at the biology of this world, even though I'm not a biologist and I don't claim to have all the intricate knowledge of all the systems that no doubt a biologist will do from his training, I can nevertheless spot systems when I see them. And one of the, if you like, the gripe that I have today is that there are few, not many, but it's not that there aren't any, but there are few biologists who really seem to appreciate the engineering mindset. They love to classify everything, and we do need classification. So clearly, the way an animal behaves here needs to be written down and understood. The way the morphology of the limb structure and everything is described in one particular creature might be different to another, and so on and so forth. But just to classify everything doesn't actually tell you really how that system works. I love thinking about flight, as you probably know, and flight is a marvel of intricate engineering when it is man-made, but the same applies to that which is created in the natural world, because the natural world displays even more sophisticated engineering. When you consider the muscle, for instance, for lifting the humerus bone in a bird, in order to enable it to have the up wing movement, so lifting the wing upwards for the upstroke, there is a special muscle which comes from the breastbone here, threaded through the coracoid, basically the sort of shoulder, the collarbone, and the ligament from this muscle is threaded through, comes up and over and lifts the humerus. So when that muscle shortens, it lifts the humerus bone. Then there is the normal pectoralis major muscle, which pulls the humerus bone down. Now, when I see that as an engineer, I can see that there is two muscles operating in tandem from the breastbone. And by the way, a bird doesn't have a diaphragm. It uses the breastbone also to breathe, which is very much a resonant behavior when it's in flight. It's obviously moving its breastbone even when it's at rest on the ground, but particularly when it's in the air, it's moving this muscle, both these muscles, to get the upstroke and then the downstroke, as well as breathing. So everything's in resonance. And immediately it's telling me this is a marvel of resonant engineering. Resonance means that you're not using more energy than you have to. You just put in a little bit of energy, and because the whole system is resonating, it just keeps going without having to input too much energy to keep it going. It's back to entropy that we were saying about earlier. So resonance is a very useful engineering principle in order to make sure that you don't have to use more power than you have to. And yet the biologist simply says, oh, that's evolved from some creature which had arms in the reptile world. Well, forgive me for using the word, but that almost becomes pathetic in engineering terms, because you've missed the whole point. Because in engineering, you need a design principle. You need to get things all together, the dimensions right. You need to get the amount of muscle, because muscles, of course, require food. So you don't want to have such a big muscle that it requires a huge amount of energy intake. But you've also got to have the muscle positioned rightly in order to use as little energy as possible, but nevertheless positioned, as I said, in a resonant position with this breastbone coming in and out, in order to get the bird operating in flight. And when you look at things from an engineering point of view, it's shouting that there is exquisite design principles. Now, what I'm very concerned about in the biology world is that design principles are never taught, at least as far as I know, they're not taught. And I believe what would be a tremendous advantage in biology is, as well as classifying everything, it's all based on the Linnaeus principle, Carl Linnaeus, who actually set this up to begin with. Oh, that's fine, I don't mind classification. Just as I classify Boeing 777s, and I classify Boeing 767s, and I classify McDonnell Douglas planes, and I classify all sorts of other planes. That's fine. Yeah, we need to know which one's which. But that doesn't tell me how they were built. That doesn't tell me the wonderful design principles that were going on in Seattle when Boeing put together their wonderful planes. That doesn't tell me how Airbus brilliantly, brought all their planes together as major competitors to Boeing. As an engineer, you need to understand design principles to actually put the wings in exactly the right place, to put the flaps in the right place, to put the winglets in the right place in order to reduce the fuel consumption at low speed. All these things we understand because we know all the design that went in Seattle, the design that went in Toulouse, whether it be Boeing or Airbus. Now we need to apply exactly the same logic to birds. I'm particularly stressing birds because that's the area that I speak on a lot, because I understand aerodynamics. I understand the way wings operate. So I do, as you can tell from the way I'm speaking, I do sometimes get a little bit frustrated when biologists just sort of sweep their arms all the way through this logic and say, it just evolved. I say, how? Tell me exactly what was the principle which enabled a frayed scale of a reptile to become a feather positioned in exactly the right place in the wing and develop the thickness such that you have an aerofoil effect in a bird's wing. I say, please tell me the detail as to exactly how this worked, when and where. And they can't tell me.